Let's configure the input impedance or the input resistance of a single stage amplifier in a common emitter configuration with RE in it unbypassed. Okay, so let's draw the circuit. And let's suppose we have plus VCC here. So we're going to be using an NPN transistor. Let's assume this is RC. Here's our transistor. Here's RE. And this is ground here. And we're going to use a voltage divider to set the voltage base for ourselves. And we're going to go from here to the base. This would be our input. This is typically our output if this is a common emitter. So this is RC, RE. Notice RE is unbypassed. And we have R1, R2. And we're interested in Rn of the stage. Stage means this whole thing. Okay, so I'm interested in the input impedance of this whole thing or this whole stage. If I had to abstract this as an amplifier, then it would be something like this. And this would be an amplifier. And it has an output and some sort of a reference, right? So we're always measuring to a reference. And these are our references right here, right? So these are our references. That is this one, right? So this will be the input. And this here will be the output, right? So we're interested in what is the input resistance of this amplifier. Well, to do this, well, first we need to convert, and we could choose which model we want to use, the pi model or the T model. I'm going to use the pi model. Okay. All right, so for the pi model, we will look at that same point, which is the input right here, and move from there. So what do we have? We have R1 in parallel with R2. This is from an AC point of view, vis-a-vis ground, right? Now, since this is the pi model, we're going to put beta RE prime, which is really beta times RE prime, knowing that RE prime is approximately 25 millivolt divided by IEQ. So we need to do a DC analysis for this circuit to come up with IEQ. And then we will have a figure for this resistance here. But from a model point of view, it is beta times RE prime, this resistance here at the base. But at the emitter, we're lifted from the ground with a resistance, RE, to ground. So that's the major difference between this circuit versus, let's say, a circuit that has a capacitor here. If we had a capacitor here, then the emitter will be to ground. But that is not the case. So this is a particular case, and this is why we're doing this analysis, to figure out what is Rn stage, right, Rn stage of this sort of, or this particular common emitter amplifier. And then we have RC to ground here. Again, this being the collector right here. Okay, so what kind of current this current generator is producing? We know this is beta little IB, and this is really current IC equals beta IB. And then we also know that we have a current little IE going through RE, and we have a current little IB. Notice little means lowercase, which means these are AC currents, right? And we can apply Kirchhoff Law here to figure out, okay, well, what is IE? We're going to need that. And let's do that. So little IE, looking at this node here, is the sum of the incoming currents. Well, that would be little IB plus little IC, right? So what is that? Well, it's IB. It's still little. I'm not going to say little anymore. Plus beta IB. Can I factor IB here? Sure. So IB times 1 plus beta. Can I approximate this to saying that this is approximately IB times beta, And you can do that if beta is much, much greater than 1. Okay? So here you add 1 to some large number and approximately be at that large number. So this here is a good approximation of IE. Okay, so how's that going to come into play? Well, let's analyze our end stage here, and let's look at it from this point. So our end stage, we're seeing 2 resistors in parallel. And this in parallel, let's assume that we have a resistance here, and we're going to call this one Rn base, which means it's the resistance seen from here. And then we have R1, R2, and Rn stage sees all these 3 as being in parallel. So Rn stage is going to be equal to R1 in parallel with R2 in parallel with Rn base. Now, some people like to say that R1 in parallel with R2, we're going to call that RB. Okay, well, that still is in parallel with Rn base. Okay, again, RB being R1 in parallel with R2. Okay, so let's evaluate now our Rn base. Let's see if we can configure our Rn base by looking at the model again. And here's the base right here, this point right here. Okay, and what we're seeing is beta times little Re prime, some resistance Re this way. And we're interested in Rn base as we see it from here. So what would that be? Well, we know we have a current IB going here. So in other words, can we assume we have a voltage Vn from here to here? Yeah, we could do that. So if we have a system that has Vn and an IB here, so what is the resistance right here? So let's call it Rn base. That's going to be equal to Vn divided by IB, right? Looking at it as a system, simply using Ohm's law. Well, that's great, but can we do something to get rid of these 2 variables and get something a little more concrete in terms of these values that we know? We know what beta Re prime is. We know what Re is. We know what R1 and R2, etc., right? So we know these values. These really depend on what you're applying in terms of Vn, and you're going to get a particular IB depending on how you set the quiescent point for the transistor, etc., right? So, and what your beta is and so on. Can we work this differently? Absolutely. Look at Vn here. It really is a composition of 2 voltages. It's this plus this, right? So let's call this one Rn base. And Vn, it really is IB times, so let me just write IB times this resistance, right? That's this voltage drop here, beta times Re prime plus the voltage drop from here to here. Well, what is that? Well, that's IE times Re. Everything divided by IB. Well, wait a minute. Don't we have IE here? Didn't we calculate that? Yep, we did. Let's go ahead and do that here. Rn base equals little IB times beta times Re prime. And again, Re prime is this thing here, plus beta IB, right? So where are we getting this from? Right here. That's IE times Re, everything divided by little IB. I'm seeing IB here, IB here, IB here. Can I get rid of it? Yeah, because you can factor these 2 divided by that. Sure enough, right? That's 1. So Rn base is going to be equal, we can factor the beta, Re prime plus Re. Aha. So Rn stage, which means the input impedance or the input resistance of the whole stage, is Rb in parallel with beta little Re prime plus Re.